Hello everyone, welcome to the 18th lecture of the course Discrete-time Markov chains and Poisson processes. So in last class, we saw the definition of stationary measure. So a stationary measure is nothing but a row vector whose size is same as the size of the state space. Its entries are all non-negative and it should satisfy the condition pi p equal to pi. Now, when the sum of the entries is equal to 1, we say that a stationary distribution is a stationary measure is a stationary distribution. Fine. And then we saw these three examples, like in example 1, there was the Markov chain had a unique stationary distribution. In example 2, the Markov chain had infinitely many stationary distributions, and in example 3, the Markov chain had no stationary distribution. The first two examples were for discrete like finite space Markov chains, but the third example was infinite space, and that is because we also saw this result that for a Markov chain with a finite state space, there always exists at least one stationary distribution. So if you have to give an example of a Markov chain which does not have any stationary distribution, then it has to be an infinite state Markov chain. Fine. So today we will continue with some more properties, some more theorems about stationary distributions. So let us start. Okay. So the first theorem, which says that let Xn be an irreducible Markov chain. That means it has only a single communicating class. Now, if pi is an invariant measure such that pi I is strictly greater than 0 for some I belonging to S, then pi k is strictly greater than 0 for all k in S. So remember, it is easy to see from the definition of stationary measure that if you look at the 0 vector, that is always a stationary measure, right? So there always exists at least one stationary measure, which is the 0 vector. But remember, this 0 vector is not a stationary distribution. Now, if you take a non-zero stationary measure, fine, that means if there is at least one component which is strictly greater than 0, and if further the Markov chain is irreducible, then each entry should be positive. Fine. So if it is an irreducible Markov chain, either all entries should be 0 or all entries should be positive. It is not, the mixture is not possible provided the Markov chain is irreducible. Then if you have a if you take a stationary measure, either all its components are 0 or all its components are strictly positive. Fine. Now let us see the proof. The proof is very simple. Now we already know that pi I is strictly greater than 0 for some I in S. We want to show that pi k is strictly greater than 0 for all k in S. So we consider a state k not equal to I. We want to show that pi k is strictly greater than 0. Now, this is an irreducible Markov chain, right? So you can go from any state to any other state in finite number of steps. So there will exist an n such that Pikn will be strictly greater than 0 because k is accessible from I. So there will exist an n such that Pikn is strictly greater than 0. And why is this true? That is because this is an irreducible Markov chain. So any state is accessible from any other state. Fine. Now, pi k, since this is an invariant measure, is equal to sum over j belonging to S, the state space, pi j Pjkn. We have already seen this. So this is not the original definition, but the original definition implies this because it's not just pi p equal to pi. It is also true that pi p to the power n is equal to pi. This is also true. Fine. So that gives you that pi k is equal to sum over j belonging to S, pi j Pjkn. but this is greater than or equal to this because all these terms are non-negative. Fine. So, this is greater than or equal to pi I, p I k n, where I is this particular I for which you know that pi I is strictly greater than 0, but now pi I is strictly greater than 0, p I k n is also strictly greater than 0. So, you get that this is strictly greater than 0, hence you finally get that pi k is strictly greater than 0. So, we have shown that if the Markov chain is irreducible, then and you are given a stationary measure where at least one component is strictly greater than 0, then all components should be strictly greater than 0. Fine? Okay? And the proof is just this 2 lines proof. It's a very simple proof which uses this irreducibility very crucially. Fine? Okay. Now, moving ahead to the next theorem. For that, now you fixed a state k. Fine. And now for each I in S in the state space, now so for each I in S, the expected time spent in I between visits to k. Now, remember what is this Tk? So, recall this definition of Tk, which was the first passage time. What was it? It was infimum over n greater than or equal to 1 such that xn is equal to k. So, the first time after 1, the Markov chain visits the state k. So, now again we are looking at Ek, that means you are starting from k. So, what is this quantity? This quantity, so let us first look at this inside thing. So, it is n running from 0 to tk minus 1 delta I xn. Remember what is delta I xn? So, delta I xn is equal to 1 if xn is equal to I equal to 0 otherwise. Correct? So, this inside summation counts the number of times starting from 0 to tk minus 1, the Markov chain is equal to I, right. So, and you are taking the expectation of this. So, this quantity is basically the expected time spent in I between visits to k. So, here because it is a discrete time, so the number of times it visits I is basically the time spent in state I. Fine. So, this gamma ik is the expected time spent in I between successive visits to k, or you can also think of the expected number of times the Markov chain visits the state I between successive visits to k. Fine. Okay. Now, we have this theorem. So, what does it say? It says that let xn be an irreducible and recurrent Markov chain, right. So, it has a single communicating class and Ek of Tk is finite for all k in the state space. Fine. Sorry, not Ek of Tk. Starting from k, you come back to A in a finite time with probability 1. That is recurrence. Fine. So, xn is irreducible and recurrent. Then gamma kk equal to 1. Now, this is very easy to see because what is gamma kk? This is the expected time spent in k between visits to k. Now, you see why it is equal to 1. So, now remember tk is the first time after 1 it visits k. So, initially that means that n equal to 0, xn is equal to k, right. Why? Because you are starting from k, and now in no other step it can be at k, because this tk is the first time after 0 it visits k. So, and since this sum is up to tk minus 1, so the number of visits to state k is just 1, fine, which is at the 0th step, and in between the Markov chain does not visit the state k, that is because tk is the first passage time. So, this gamma kk equal to 1 is trivial. Anyway, we will not see a complete proof of this theorem. Now, the second one says that this, now if I look at this row vector which is gamma ik, fine. So, I can look at this row vector gamma ik where I belongs to S. Now, it says that this row vector is a stationary, it satisfies this stationary condition. Anyway, see, this is, all these gamma i's are non-negative because you are, this number of visits, that's obviously is a non-negative thing, you are taking expectation of that. So, anyway, gamma ik is greater than or equal to 0, that is not an issue. What this point 2 is saying is that it satisfies this stationarity condition. And also the third condition says it is not just greater than or equal to 0, but each gamma ik is strictly greater than 0 and also it is finite for all I in S. Fine. So, what this theorem is telling you, if you define gamma ik in this way, then this is a stationary measure or an invariant measure where each component is strictly positive. Fine. So, gamma k defined in this way is a stationary measure or an invariant measure, and also one more property. So, you have this thing that this gamma kk equal to 1. So, it is a stationary measure such that the kth component is equal to 1. Fine. That is the content of this theorem. Fine. So, now we move on. So, why did we define this spatial stationary measure? Now, the next theorem says that let Xn be an irreducible Markov chain. Again, so it has only a single communicating class. Now, fix a state k and let pi be an invariant measure with pi k equal to 1. Fine. So, we saw in the previous theorem that this gamma k was an invariant measure with gamma kk equal to 1, or the kth component is equal to 1. Now, suppose we look at some invariant measure, we do not know whether it is exactly that gamma kk, it is some invariant measure with this property that pi k equal to 1. Fine. Then pi is greater than or equal to gamma k. What does that mean? So, what is this meaning of greater than or equal to? That means pi I is greater than or equal to gamma k I for all I in S. That is the meaning of entry wise. Fine. So, what this says is that if you take any other invariant measure with the condition, so this condition is important that pi k equal to 1, then pi is greater than or equal to gamma k. So, in that way this gamma k is what is called a minimal stationary measure. Again, it is just a terminology, you do not need to bother about that, but the important thing is this inequality, that if pi is any invariant measure with this constraint that pi k equal to 1, then that pi has to be greater than or equal to gamma k entry wise, or in other words, this should be true. If in addition the chain is also recurrent, so if in addition the chain is also recurrent, then pi is actually equal to gamma k. Fine. So, if you are working with, if Xn is irreducible and recurrent, then what this theorem tells you that this gamma k is the only invariant measure with gamma k equal to 1, or with the kth component equal to 1. Fine. So, if it is just irreducible, then you take any invariant measure with the property that the kth component in 1, then pi should be, that invariant measure pi should be greater than or equal to gamma k. If in addition the chain is also recurrent, then pi is actually equal to gamma k. Again, this equality means component wise, that means pi I is equal to gamma k I for all I in S. Fine. That means if you if Xn is an irreducible and recurrent Markov chain, then this gamma k, which we defined here in this way, is the only invariant or is the only stationary measure with the property that the kth component is equal to 1. So, if I give you a stationary or invariant measure with, and I tell you that its kth component is 1, and also if you know that it is an irreducible and recurrent Markov chain, then straight away you can say, okay, this stationary measure is actually this gamma k which we defined in the previous slide. That is what is the content of this theorem. Fine. Now, this theorem gives us a kind of corollary which we write here as a remark. So, let Xn be an irreducible and recurrent Markov chain. Let pi and mu be two non-zero invariant measures. Fine. Now, what is the meaning of non-zero invariant measures? That means each component is strictly greater than 0. See, just non-zero means it tells you that there will exist at least one. So, strictly speaking, non-zero invariant measure means there will exist at least one component which is strictly greater than 0. But since you have irreducibility, now from the first theorem what we proved today, we know that if it is irreducible Markov chain, then if you take a stationary measure, either it is the 0 measure or each component is strictly greater than 0. So, the setup that we are looking here, since it is irreducible, so when we say pi and mu be two non-zero invariant measures, that means each component is strictly greater than 0. But in general, if I just say pi is a non-zero invariant measure, that means there is at least one component which is strictly greater than 0. But irreducibility forces that each component has to be strictly greater than 0. So, pi and mu are two such non-zero invariant. So, suppose pi and mu are two non-zero invariant measures, then there exists C such that mu equal to C pi. Fine. Now, let us see the proof of that. So, okay, before going to the proof of that, so what is it saying? That if you are having an irreducible and recurrent Markov chain, fine, then and if pi and mu be two non-zero invariant measures, then one is a scalar multiple of the other. So, if you have a irreducible and recurrent Markov chain, then you take any two non-zero invariant measures, one is a scalar multiple of the other. Fine? Okay. And also you can easily check, so this C actually will be not equal to 0. Fine? Okay. Now, what is the proof of that? So, for that again fix a state K. Fine. Now, by this above theorem, remember it says that if you have an irreducible and recurrent Markov chain such and you are given an invariant measure whose kth component is equal to 1, then that is equal to gamma k. Now, you are given these two invariant measures pi and mu, but you do not know whether their kth component is equal to 1. But there is a way to make their kth component equal to 1. You divide by pi k. So, you look at the measure. So, each component you divide by pi k. Then, since each component you are dividing by pi k, so the kth component now will become 1, right? Because it will be pi k over pi k, and hence the kth component will become 1. So, pi over pi k, now initially we did not know whether for pi the kth component is equal to 1, but now if we look at this slightly modified invariant measure pi over pi k. Now, remember if something is an invariant measure, so if pi is an invariant measure, then C times pi is also an invariant measure. This you can easily check. If you take an invariant measure, then any scalar multiple of that is also an invariant measure. So, if I divide by 1 over pi k, it still remains an invariant measure, but now the advantage is this modified measure for this the kth component is equal to 1. Now we are Xn is an irreducible and recurrent Markov chain, and this pi over pi k is a stationary measure with kth component equal to 1. So by this theorem, this has to be equal to gamma k. Fine. Now similarly, if I look at mu, then again if I look at mu over mu k, that is again an invariant measure whose kth component is equal to 1. But again by this theorem, this mu over mu k should be equal to gamma k. And remember, like we can easily divide by this pi k or mu k because these are two non-zero invariant measures. So each component is strictly greater than 0 since we also have irreducibility. So pi over pi k is an invariant measure whose kth component is 1. Mu over mu k is an invariant measure whose kth component is 1. We are having, so the chain Xn is irreducible and recurrent. So by this theorem above, we get that both of them should be equal to gamma k. But now from this, you just take this pi k to that side. What we get is mu equal to mu k over pi k times pi, or it is equal to c pi, where c is equal to this. And since this mu k and pi k are both non-zero, so this c is not equal to 0. So what it basically says that mu equal to c pi, at the same time you can write it as mu is equal to 1 over, or pi is equal to 1 over mu, 1 over c times mu. So if you are having an irreducible and recurrent Markov chain, and if you have two non-zero stationary measures, then they are actually scalar multiple of one another. So in this way, you have kind of uniqueness. So see, if you have an invariant measure, its scalar multiple is again an invariant measure. That is in general true. Fine. But what this theorem is telling is that if you have an irreducible and recurrent Markov chain, then any two invariant measures and you take any two non-zero invariant measures, then one is a scalar multiple of other. So in that way, again, there does not exist a unique invariant measure, but if you take any two invariant measures, one is a scalar multiple of the other. So in that sense, so you have this kind of a weak uniqueness that one is a scalar multiple of the other, provided the chain is irreducible and recurrent. So you need these two additional conditions on the Markov chain. If it is any Markov chain, then such a thing is not true. But see, what is always true is that if you have an invariant measure, any scalar multiple is again an invariant measure. Fine. But what this theorem is telling is that, okay, if you have an irreducible and recurrent Markov chain, then any two non-zero invariant measures are scalar multiple of one another. Fine. But remember, the two important assumptions are required: irreducibility and recurrent. Fine. Okay. So moving on. Now, so till now we have classified states as recurrent and transient. For recurrent, starting from I, the probability that it will come back to I in a finite time is 1. So probability, with probability 1 starting from I, it will come back to I in a finite time. And if it is transient, then there is a positive probability that starting from I, it will never come back to I. So for recurrent, you have pi of ti less than infinity is equal to 1. And for transient, pi of ti less than infinity is equal to 1 for recurrent, and for transient, pi of ti less than infinity is less than 1. So there is a positive probability that pi of ti equal to infinity. So just let me write it here. Pi of ti less than infinity is equal to 1, and pi of ti less than infinity is less than 1. So this is recurrent and this is transient. Recurrent. Fine. Now, you will see that we will further classify recurrent states into two more subcategories. What are those? So, a recurrent state I is said to be positive recurrent if mi, which is equal to ei of ti, is less than infinity. That means that the expected time in which it will come back, that is also finite. Fine. And if I is not positive recurrent, then it is called null recurrent. So, see, if I give you a non-negative random variable which is finite valued, it is not guaranteed that its expectation will be finite. Its expectation can be both finite as well as infinite. So, now if I look at this ti, which is the first passage time to I or the first return time to I, now recurrent means it's a finite random variable with probability 1. But if just finite random variable with probability 1 doesn't guarantee that its expectation is also finite. So, if its expectation is also finite, then you say it is positive recurrent, and if it is not, then you say it is null recurrent. Fine. And what is like how you should think about it, or what is the intuition? So, positive recurrent means that it will come back. So, recurrent means it will come back starting from I, it will come back to I in finite time with with probability 1. But null recurrent means, okay, with like it might take actually a very long time with high probability. Fine. So, that is why when you look at this weighted, what is expectation? Expectation is basically weighted average. So, null recurrent means, okay, it is finite, but its expectation is not finite. So, the intuition is that, okay, it will come back in finite time, but it will, see, finite doesn't mean how big or small it is. Just finite means, okay, it's not infinity, right? But null recurrent means, okay, that again, that this is the way, or this is the way you should think about it. This is the intuition that, okay, it will come back in finite time, but with a substantial probability it will come back. It will take very long to come back. Fine. That is why the expectation is not finite. So, if ei of ti is finite, we say that it is positive recurrent. If ei of ti is not finite, or it is equal to infinity, we say it is null recurrent. So, recurrent states we have further classified into two subcategories, namely positive recurrent and null recurrent. So, the initial division was recurrent and transient, and now we further divide recurrent into positive and null. Fine. So, initially we divided it into recurrent and transient, and now we further subdivide it into positive and null. Fine. Okay, good. So, that is the definition of recurrent state, but now why suddenly we have brought in this positive recurrence and null recurrence? Because it has very close connection to this stationary distribution. Now, that brings us to the last theorem of today's lecture, which says that let Xn be an irreducible Markov chain. Fine. Then the following are equivalent. What is the meaning of the following are equivalent? That means all these things. So, 1 implies 2, 2 implies 3. So, all these are if and only if. So, all these are if and only if. So, 1 implies, sorry. So, again, so it says that 1 implies 2, 2 implies 3, 3 implies 1. So, all these, like if you assume 1, then the other is true. That is the meaning of that the following are equivalent. So, let Xn be an irreducible Markov chain, then the following are equivalent. What are the following? What are those statements which are equivalent? Every state I is positive recurrent, some state I is positive recurrent, the Markov chain has a stationary distribution pi. Fine. So, that means if every, remember we are in an irreducible, we are working with an irreducible Markov chain. It says that if every state I is positive recurrent, then some state I is positive recurrent. Now, this is kind of trivial if every state is positive recurrent, but some state I is positive recurrent. But it is also saying the other way is true, that if some state I is positive recurrent, then every state is positive recurrent. Not only that, these two statements are also equivalent to the statement that the Markov chain has a stationary distribution. So, for example, if you know that every state in an irreducible Markov chain is positive recurrent, then you know that the Markov chain has a stationary distribution. So, this gives you a sufficient condition. Fine. Not only sufficient, because this is an if and only if condition. So, if you are in an irreducible Markov chain, then if you can show that each state is positive recurrent, then you know that it has a stationary distribution. But not only that, it's not that it just has a stationary distribution. It says that moreover, when 3 holds, pi I is equal to 1 over mi for all I in S, where mi is this ei over ei of ti. Fine. So, again, let me try to explain this, because this is a very important theorem. So, it says that if xn is an irreducible Markov chain, then all these statements are equivalent. So, if you assume one, then the other is true. So, all these are if and only if. So, it says that every state I is positive recurrent, some state I is positive recurrent, the Markov chain has a stationary distribution pi. So, say for example, if you know every state I is positive recurrent and it is an irreducible Markov chain, then the Markov chain has a stationary distribution. Similarly, you don't actually need that every state is positive recurrent. If you know that just some state I is positive recurrent and it is an irreducible Markov chain, then also you know that the Markov chain has a stationary distribution. But not only that, under irreducibility, it also tells you that this stationary distribution is actually, so it tells you what that stationary distribution is, or in other words, if it is an irreducible Markov chain, then there can exist at most one stationary distribution, right? So, it says that when 3 holds, that means when the Markov chain has a stationary distribution. So, suppose you are having an irreducible Markov chain. Now, then just look at this statement 3. It says that the Markov chain has a stationary, if the Markov chain has a stationary distribution, then it is necessarily 1 over mi, where mi is this ei of ti. So, it tells you that if it is an irreducible Markov chain, then there can exist at most one stationary distribution. So, remember, for any Markov chain, I said 3 possibilities are true. Either it is 1, or either it is 0, 1, or infinity. But if it is an irreducible Markov chain, the only possibilities are 0 and 1. Infinity is not possible. If it is an irreducible Markov chain, there will exist at most one stationary distribution. Fine. And it also tells you, if it exists, what that stationary distribution is. So, pi I is 1 over mi, where mi is nothing but ei of ti. So, you see how this stationary distribution and positive recurrence is connected. So, all these statements are if and only if. So, another implication of this is, so if I tell you xn is an irreducible Markov chain and it has a stationary distribution I, then from that you can straight away say that all states are positive recurrent. That is like 3 implies 2, 3 implies 1, sorry. So, because all these are if and only if, so if it is an irreducible Markov chain and I say that the Markov chain has a stationary distribution pi, that straight away tells you that every state is positive recurrent. So, if it is an irreducible Markov chain, then there can exist at most one stationary distribution. But remember, if it is a finite state Markov chain, we have already proved that there will exist at least one stationary distribution. So, if it is an irreducible finite state Markov chain, then there exists a unique stationary distribution. Fine. So, if it is finite state Markov chain, that implies plus irreducible, sorry. So, finite state Markov chain plus irreducible implies existence of unique stationary distribution. Fine. So, if it is an infinite state, but is irreducible, there can exist either 0 stationary distribution or 1 stationary distribution. If it is a finite state Markov chain plus irreducible, then there exists exactly 1 stationary distribution. So, you now know a case where you have both existence and uniqueness. What? So, if you take a finite state irreducible Markov chain, then it has a unique stationary distribution. But if it is not finite, if the state space is not finite but infinite but still irreducible, then you know that if there exists a stationary distribution, then that will be unique. For infinite state Markov chain, existence of stationary distribution is not guaranteed, but if it exists, there will be unique. For example, you saw this okay, so we'll come to one example slightly later, but if it is an irreducible infinite state Markov chain, then existence is not guaranteed, but uniqueness is guaranteed. So, if there is one, there will be exactly one. But if it is a finite state Markov chain, then there will exist exactly 1 stationary distribution. So, finite state Markov chain plus irreducible implies existence of a unique stationary distribution. That's one implication of this theorem. Another implication is this remark. What it says that this positive recurrence and null recurrence are class properties. Because why? You see again, so if it is an irreducible Markov chain, then that means, so it's because that is coming from 2 implies 1. So, it says that if some state I is positive recurrent, then every state I is positive recurrent. So, it is not possible that, again, why I am saying class properties, irreducibility, here it says about irreducibility, but again, if I can say, for example, I start with a positive recurrent state, fine. Now, I look at the class of that. Now, since it is positive recurrent, so it is recurrent, okay. So, if I just look at the class of that, that is a closed class. So, I can think I can restrict my Markov chain on that. So, it will be just an irreducible Markov chain on that class, fine. So, now it tells you that in that class there cannot be any null recurrent state. Why? Because of this theorem. It says that if some state I is positive recurrent, then every state I is positive recurrent. So, till now we knew that this transience and recurrence are class properties, but what we get from this theorem is that both positive recurrence as well as null recurrence is also class property. So, if you have a communicating class of recurrent states, then either all the states will be positive recurrent or all the states will be null recurrent, fine. Okay. Now, we will finish today with 2 examples. First, recall the simple random walk. Now, we have proved that asymmetric simple random walk is transient, right? We have proved that. Now, thus by previous theorem, it cannot have a stationary distribution. Why? Because the previous theorem said that if you have an irreducible Markov chain, remember, asymmetric simple random walk is also irreducible. So, if you have a irreducible Markov chain, then if it has a stationary distribution, then all states has to be positive recurrent. But for an asymmetric simple random walk, which is also irreducible, forget positive recurrent, we know that all states are transient. So, it cannot have a stationary distribution. So, you see, for an infinite state Markov chain, even if it is irreducible, it is possible that it may not have a stationary distribution. But if it has, then it has to be unique and it is given by 1 over mi. Fine. So, here is an example of an infinite state Markov chain which does not have a stationary distribution, which is this asymmetric simple random walk. And why is that? Because each state is transient. And the previous theorem already told us that if it has a stationary distribution, then each state has to be positive recurrent. Fine? Okay. So that's example 31, the first example, which was of asymmetric simple random walk. Now the second example, here we look at the simple symmetric random walk. Now for simple symmetric random walk, we know that all states are recurrent. But now the question are whether they are positive recurrent or null recurrent, because now we have also know that positive recurrence and null recurrence are also class properties. So either all states will be positive recurrent or all states will be null recurrent, because a simple symmetric random walk is irreducible. Fine? Okay. Now let us try to examine what those states are, positive recurrent or null recurrent. Now for simple symmetric random walk, we have shown that all states are recurrent. Now if I look at this pi I, so I am looking at this vector of all ones. So it will be an infinite vector. So it will go to both sides, right? Because in this case, for a simple symmetric random walk, the state space is the set of all integers, which is an infinite set. So if pi I equal to 1, or in other words, if I look at this infinite vector of all ones, then it satisfies this pi I equal to half pi I minus 1 plus half pi I plus 1. And why this? Remember, so this is precisely the stationarity condition for simple symmetric random walk, because again, what is, so pi I, what it should be? So I said, so in the summation is over only those things like from where you can come to I, right? So now in a simple symmetric random walk, you can come to I either from I minus 1 or from I plus 1. So you come from I minus 1 with probability half, and you come from I plus 1 with probability half, right? So the stationarity equations become this pi I equal to half pi I minus 1 plus half pi I plus 1. And if I take this pi I equal to 1 for all I, then these equations are satisfied. Or in other words, this is a stationary measure for simple symmetric random walk. Also, this is a non-zero stationary measure. Fine. Now, again, so 0 is always an invariant measure. Now, remember, we are trying to, so what we are initially trying to see that whether a simple symmetric random walk has a stationary distribution or not. Now, what is a stationary distribution? A stationary distribution is also a stationary measure with the added condition that the sum of the entries has to be 1. But now if the sum of the entries has to be 1, it cannot be the 0 stationary measure. It has to be a non-zero stationary measure. Fine. Now non-zero stationary measure, a simple symmetric random walk is irreducible. So non-zero means each component has to be positive. So now we already have a stationary measure, which is the vector of all ones. So if there exists a stationary distribution or an invariant distribution, then that also has to be a stationary measure where each component is strictly greater than 0. But now this is an irreducible and recurrent Markov chain. Now we have seen this, that if it is an irreducible and recurrent Markov chain, then if we have two invariant measures or two stationary measures, then one is a scalar multiple of other. So if you have a stationary distribution, that should be a scalar multiple of this. So again, it should be of the form, say, C, C, C. So it should be a vector of all C's for some C strictly greater than 0. Obviously, C cannot be 0 because then the sum will not be 1. But again, if every component is same, then the sum will not be equal to 1. Fine? So, and then again, another way of saying this, that since any invariant measure must be a scalar multiple of pi, but now pi is all 1, so this sum is infinity. So if you and now if there has to exist a stationary distribution, it should be some c times pi I, right? So the components should be of the form c times pi I, but then the sum that simply c will come out, but since this series or this sum is infinite, by multiplying by any non-zero c, you cannot make it equal to 1. Fine. So the thing is that if there has to be a stationary distribution in this case, all its components has to be equal. But if all its components are equal, then that sum cannot be equal to 1. In fact, that sum will be equal to infinity. So there cannot exist a stationary distribution. So the main thing that we are using here is that since this is an irreducible and recurrent Markov chain, so and we have already found out a stationary measure, which is the vector of all ones. So the stationary distribution has to be a scalar multiple of that. So it has to be of the form of all. So it has to be a vector where all components are equal. If all components are equal, then the sum of the components cannot be equal to 1. It will be equal to infinity. We have seen this thing before as well. So that if all components are same, the sum cannot be finite. Fine. Or other words, sum cannot be equal to 1. So forget 1, it cannot be even finite. So in this case also, there cannot exist a stationary distribution. So for a asymmetric simple random walk, it's very simple. We can say very easily that there does not exist a stationary distribution because all states are transient. But for simple random walk, we need to do a little more. How we are claiming, so but we finally see that even for a simple symmetric random walk, there does not exist a stationary distribution. But since there does not exist a stationary distribution, all states are null recurrent. Why? Because if the states are positive recurrent, then again, if I go back to this theorem, it says that if every state I is positive recurrent, then the Markov chain has a stationary distribution. But we have shown that for a simple symmetric random walk, there does not exist a stationary distribution. So the states all has to be null recurrent, because if the states are positive recurrent, then the theorem that we just saw in previous slide tells you there has to exist a stationary distribution. In fact, there will exist, because we are in this irreducible setup, there will exist exactly one stationary distribution. But we know that there exists, but we have shown that there cannot exist a stationary distribution. So all states of a simple symmetric random walk are null recurrent. So for both simple symmetric random walk as well as asymmetric simple random walk, there does not exist a stationary distribution. So both these are examples of infinite state irreducible Markov chains where stationary distribution does not exist, right? So when it is infinite state, then it is possible that stationary distribution does not exist. But if it exists, and we also know that it is irreducible, there will be exactly one. Fine. So existence is not guaranteed, but uniqueness is guaranteed. But for finite state Markov chain, both existence as well as uniqueness is guaranteed if it is irreducible. Fine. So that's all. So we will stop here today. Thank you all.